This talk is about indium gallium nitride photovoltaics with composition grading. C.Jayant Praharaj, band photonics materials. So the talk basically covers various kinds of grading like doping grading and polarization grading in photovoltaic solar cells made from this material system. It talks about the physics of polarization and light matter interaction in these solar cells. So the slide here basically shows the wavelength and energy range of indium gallium nitride alloys. And as you can see on the figure in the left here, the indium gallium nitride alloy system covers the band gap range or energy range from the infrared to the ultraviolet through the visible. And you can see that the indium nitride band gap is about 0.7 to 0.8 electron volts, while the gallium nitride band gap is about 3.4 electron volts. The actual alloys have some bowing that is not shown here, but the trend here gives a very good idea of the kind of band gap variation that takes place with the various alloy compositions in indium gallium nitride. Also in the same group of material systems is aluminum nitride, which has an even wider band gap of 6.2 electron volts. Now, we do not cover aluminum gallium nitride alloys in this talk. However, there are many photonic and electronic devices that can be made from aluminum gallium nitride as well. So we talk about a specific class of photonic or optoelectronic devices made from the indium gallium nitride alloy system, and that covers this range from 0.7 or 0.8 electron volts to 3.4 electron volts. And you can also see in the figure the effective mass trends in this material system. And as the figure shows, the effective mass kind of tracks the band gap. And this tracking is consistent with the K dot P theory of effective mass in these semiconductors. So the other thing to mention is that graded devices are ideal for capturing solar radiation with the minimum losses to the lattice. And we will see more of this physics later on in this talk. This slide shows a comparison between the group 3 nitride semiconductors and other common semiconductor systems as far as band gap and lattice constants are concerned. You can see that the group 3 nitride semiconductors typically is on the lower end of the lattice constant spectrum and on the higher end of the band gap spectrum. This kind of trend is also expected from band structure calculations like tight binding calculations or density functional theory calculations in this kind of material system. And as you can see, the group 3 nitride material system spans the range through the visible from the infrared to the ultraviolet, while the you can see that the other material systems like the arsenides and the phosphides cover only part of the visible spectrum and then the infrared part of the spectrum. And you can also see that these dotted lines that are shown here correspond to indirect band gap materials. And as we'll see later, direct band gap materials are better at absorbing solar radiation in the sense that they have higher absorption coefficients. So the group 3 nitride material system is all direct band gap. while some of these other materials are indirect band gap. Some of them are direct, or some of them are indirect band gap material. So that is a consideration when it comes to determining the absorption coefficients of these semiconductors, and when it comes to designing solar cells or photovoltaic cells from these semiconductors. And this slide also shows silicon and germanium indirect band gap semiconductors in the same slide. And also shown on the right here are some of the a wider range of material systems as far as band gap and lattice constants are concerned. So you can see the same kind of trend, and you can see that the nitride system is very ideal for realizing solar cells because they offer this design convenience over a wide range of energies that covers the solar spectrum. On this slide, we show some of the band structures in these materials. And as you can see, the band structure is crucial to determining many material properties like mass, mobility, and optical properties like absorption coefficient, complex dielectric constants, etc. As the bottom slide show basically the valence band spectrum, while this dispersions, while the upper slides, the upper panels show the conduction band spectrum. This slide, the band gap is normalized, but you can see that the effective masses are different for these different semiconductors. And so band structure determines effective mass, and it also determines scattering rates, and therefore band structure affects mobility. And the band structure determines density of states and joint density of states that affect the absorption coefficient in these materials. This slide, we show a comparison between the woodsite and cubic or zinc blende. So the group 3 nitride semiconductors are found in both the woodsite or hexagonal crystal structure form, and also the, however, the woodsite form is the thermodynamically more stable form and is the easiest to grow scientifically and technologically. But the cubic form can also be attained by careful optimization in some cases. And you can see there is a comparison. There's a lot of similarity, but however, there are some subtle differences as far as effective masses, etc., and the band ordering, etc., are concerned in these semiconductors. And for optical properties, it's not just the properties close to the conduction band minimum and valence band maximum, but however, far deep inside the band also, because absorption can take place not just close to the band gap, but also far above the band gap. And therefore, the density of states deep inside the bands, inside the valence band and inside the conduction band often become very relevant for determining optical properties like absorption coefficient. So that's a thing to keep in mind while designing solar cells from this kind of material system. We also show the phonon dispersion in the group 3 nitrides, the gallium nitride, aluminum nitride, and indium nitride. You can see typically compared to material systems like the arsenides and the phosphides, these materials have higher phonon energies. This basically shows the dispersion. Now, phonon dispersion and other material parameters related to the phonon in these materials determine things like scattering rates and mobility in these materials. And so it's not just the effective mass, but also the phonon dispersions and the phonon-related material parameters that are relevant for determining material constants like mobility, which then decide device characteristics in devices made from these materials. This slide shows some physics of scattering rates and mobility in these semiconductors, and it shows the scattering rates and mobility of electrons and holes. And you can see there are different scattering mechanisms. There are acoustic phonon scattering, there is optical phonon scattering, intervalley scattering in these materials, and you have different kinds of scattering rates as a function of energy. So typically, there is also impurity scattering, not shown here. Impurity scattering typically decreases with energy, while the phonon scattering rates typically increase with energy. And the figure on the left shows phonon scattering rates increasing with energies. And the phonon scattering consists of phonon absorption scattering and phonon emission scattering. So it's sum of those two scattering rates that determine the phonon scattering rates. And as you can see, these are the various kinds of phonon scatterings that happen in these materials. Also mentioned here is the dislocation scattering. And in these materials, there is the dipolar as well as the quadrupolar contribution to various kinds of phonon scattering rates for holes and for electrons as a function of energy. And you can see that there is some modification that takes place due to quadrupolar contribution in addition to dipolar contributions in these materials. So these are all scattering rate parameters that affect the mobility parameters that enter into device equations of any kind of device, whether you make electronic devices or optoelectronic devices in these materials. These scattering rates determine things like mobility, and then the various device equations that enter into devices like the solar cells that we consider in this talk. This slide shows the nature of solar radiation. It shows the nature of solar radiation both in outer space, just beyond the top of the Earth's atmosphere, and also at the surface of the Earth. So the top curve is basically the solar radiation beyond the top of the Earth's atmosphere. It basically is a version of the original solar spectrum emitted by the sun. And as you can see, the bottom curve shows the spectrum received at the surface of the Earth, and this is the so-called AM 1.5 radiation. And as you can see, it has several dips. And this is the solar spectrum received at the surface of the Earth after molecular absorption in the atmosphere. So there are diatomic, triatomic, and other kinds of molecules in the atmosphere that have specific absorption bands for different parts of the solar radiation. For example, they can have absorption bands in the infrared and in the ultraviolet. And so these absorption bands manifest themselves as these dips in these incident solar power spectrum as a function of wavelength at the surface of the Earth. So these incident power solar spectrum are very relevant when we design solar cells, because we typically have different layers that focus on capturing different parts of the solar spectrum and then converting them to useful electronic currents and electrical energy. Other things to mention here are that when the photons, so the solar photons are incident on a semiconductor, some of the photon energy is transmitted and goes into the semiconductor and then gets absorbed inside the semiconductor, but some of it gets reflected. And the photon reflectivity makes it necessary to use anti-reflective coatings in order to minimize the reflection losses and to make sure that more of the photon radiation gets into the material in order to be absorbed. The other thing is that transparent conducting electrodes are necessary in order to reduce electrode reflection and absorption. And this works by having the right spacing between plasmon frequency and solar radiation. So what happens is that the dielectric function in these conducting electrodes is a function of frequency, and that function depends on the plasmon frequency, and it actually switches between negative and positive as a function of frequency as we vary the frequency. And typically, in order to get low reflection, we want positive values of the dielectric function. And so the value of the plasmon frequency becomes crucial while deciding when we are able to get low reflection. And we want to design the transparent conducting electrode so that it has the plasmon frequency so that in the range of the solar radiation energies, the reflection is minimized. So that is the concern for designing transparent conducting electrodes. This slide, we show some details about typical current voltage characteristics of the IV curves of the solar cell under illumination. So you can see that under illumination, the current density has components that, for example, there is a short circuit current density component, there is a dark current component, and then there is an exponential dependence on voltage along, and inside the exponential dependence, there is a so-called ideality factor or eta factor of the solar cell device. And it is this kind of equation that determines the kind of current versus voltage under illumination that you get from the solar cell, and that decides what kind of power, electrical power you can get out of the solar cell. Typically, to get good power conversion efficiency, we want high value of the short circuit current, and we want a low value of the dark current. Now, the short circuit current is typically maximized by lowering band gap. What happens is that when you lower band gap, then more of the solar energy spectrum can get absorbed, and that leads to more electron and hole, photo-generated electron and hole pairs. And these electrons and hole pairs are swept away by built-in electric fields, and then they are collected as short circuit current. Now, while the dark current is minimized by having a wider band gap. So we need to do both kinds of things in order to improve the conversion efficiency in these solar cells. So what we need is a combination of wide and narrow band gap material within the same structure or within the same solar cell. And that is the way to increase conversion efficiency. So that typically leads to some careful optimization and leads to multi-layer design or to graded composition design. So this talk focuses on graded composition. So that is a way to achieve these dual goals of maximizing the short circuit current and minimizing the dark currents. Now, the ideality factor depends on things like dislocation recombination, and that is a function of the epitaxial layer and the substrate material, etc. And those things need to be kept in mind as well in order to get the maximum solar cell power conversion efficiency. More details about the optimization of short circuit current and dark current using combinations of wide and narrow band gap. So the use of wide and narrow band gap in the same structure comes with some added complications like barriers to current flow. So that can work towards decreasing overall efficiency. So we need careful optimization of things like band discontinuities or grading of band discontinuities, etc., or grading of the valence band profiles and conduction band profiles in order to get the best power response from these solar illuminated solar cells. Now, possible types of structures that can be used to achieve solar cells are, for example, double heterojunction structures, then some graded layer structures, and some multi-quantum well absorption layers. Now, in this talk, we focus mainly on graded layer structures. Graded layer structures have the advantage that they achieve conduction band profile grading and valence band profile grading without major band discontinuities and without major barriers to current flow. However, they require quasi-continuous grading, and that is much more difficult to attain technologically. For example, molecular beam epitaxy or metal organic chemical vapor deposition epitaxy that is used to realize these devices can have complications when we try to realize these quasi-continuous grading. Well, we have a simpler technology when we try to use something like double heterojunction structures, but they have band offset discontinuities that introduce barriers to current flow. So we focus on the graded layer structures. Now, it is also possible to have multi-quantum wells inside the absorption layers. And the multi-quantum wells basically modify the absorption characteristics and help achieve some of the goals of getting better absorption. However, again, multi-quantum wells are more difficult to fabricate, more difficult to grow using the available epitaxial growth techniques. This slide shows the typical structure of an indium gallium nitride solar cell. And the layer shown in red here is the major light or photon absorbing layer. And it's also a drift. So in this layer, we have a photon absorption from the solar cell radiation, and we have photogenerated electrons and holes. And there are built-in electric fields. For example, we can have P-N junctions, or P and N type doping in homogeneities in these devices that can lead to inbuilt electric fields. And these built-in electric fields provide the drift layer in order to make the photogenerated electrons and holes drift in opposite directions and then to be collected as a short circuit current or to be collected as solar cell device current under load operation. So these layers need careful optimization. And then we have both sides of the major absorption and drift layer. We have absorption and dark current reducing layers. So these typically have different band gaps, typically tend to have wider band gaps compared to the absorption and drift layer. And then we have a front contact and anti-reflecting layer. And we, in this diagram, the incident photons are incident from solar radiation and incident from the top. Then we have front contacts, which also has anti-reflecting layer. Then these anti-reflecting layers are typically achieved by having a dielectric constant or dielectric function grading. So we have multi-layers in order to achieve anti-reflecting layers. And then we have the transparent conducting electrodes as front contacts. And then we have a back contact. Now, these different layers typically have indium and gallium, different indium and gallium composition, as we just mentioned. This slide talks more about the grading in an indium gallium nitride solar cell. So you can see that in the light absorption and drift layer, you can have quasi-continuous grading. Now, this can be an intrinsic layer or with quasi-continuous grading, or it can be it can have multi-quantum wells. In this talk, we focus more on the quasi-continuous grading kind of solar cells using these structures. Some more details about contact. So the front contact, so we have the you need anti-reflecting layers, as we just mentioned, which use these dielectric function grading. Now, typically some thin indium gallium nitride cap layer may be used to get lower contact resistance to the p-type layer. So for instance, if the top layer is p-type, then we may need a cap layer because as we'll see in more detail later, the p-type layer is more difficult to get contacts to and these kind of materials. And so the cap layer causes polarization induced interface sheet charge, and that helps get lower tunneling barrier thickness, and that helps lower the contact resistance in these materials. So that is a consideration to keep in mind while designing contacts in these indium gallium nitride solar cells in order to reduce voltage drops and to get maximum power conversion efficiencies. This slide talks about the complex dielectric function and absorption in these kind of materials. So the equation on the top here shows a typical absorption coefficient profile close to the band gap and just above the band gap. And when just above the band gap for direct band gap materials, and you can see that it has a square root of energy dependence. So it's basically goes as a square root of the photon energy minus the band gap energy times some constant. And then below that, we show the absorption coefficients in indirect band gap materials when there is a phonon absorption. So indirect band gap materials need phonon-assisted photon absorption, and they have lower absorption coefficients, and they have the forms shown here. Now, also the thing to keep in mind is that for the direct bandgap material, while the absorption coefficient has this kind of dependence for a photon energy is just above the band gap, when you have photon energy much higher than the band gap, then they have much more complicated dependence on the energy. So the physics here is that there is a joint density of states between the conduction band and the valence band, and this joint density of states is a complicated dependence, especially as we go higher in energy, because the conduction band's dispersion spectrum has complicated features like Van Hove singularities, and so does the valence band dispersion spectrum. And so far above the band gap energy, the absorption coefficient can have a more complicated dependence. So indirect bandgap materials need phonon-assisted photon absorption, and they'll have lower absorption coefficients, while direct bandgaps have intrinsic photon absorption. So that is relevant for solar cell design. The indium gallium nitride solar cells we consider here are all made from direct bandgap materials. There is some concern that when we alloy and we change the composition to have alloy layers or alloy quasi-continuous layers in this design, what is the nature? And so there is a lot of experimental and theoretical evidence that it remains a direct band gap in this indium gallium nitride material system. So this slide shows some physics of transition rates and emission and absorption in these materials. So you basically have transition rates determined by what are called matrix elements of perturbation Hamiltonian in these materials. And then we have energy conserving delta functions that come from quantum mechanical time dependent perturbation theory. Then we have the Fermi occupation factors, and then we have joint density of states, etc. in these materials, and they can be put in this form. And the perturbation Hamiltonian has the momentum operator in it, and therefore the momentum matrix element becomes crucial for determining emission and absorption rates in this kind of solar cells and in this kind of layers which go into forming the solar cells. And these are the basic fundamental considerations that go into determining complex dielectric constant, real part of dielectric constant, imaginary part of dielectric function, and the absorption coefficients as a function of energy in these materials. This slide shows some calculations and some experimental determination of absorption coefficients in various kinds of semiconductors. So on the left, we show direct bandgap gallium arsenide and indirect bandgap silicon, and you can see the absorption coefficient as a function of energy with a bandgap edge. And on the right, we show indium gallium nitride material system with different indium compositions. We show 4 different indium composition. And as you can see that as the indium composition percentage increases in these materials, the absorption shifts to the right along the energy axis. And you can see there is an absorption edge, and then there are complicated features far above the band gap in these alloys. And you have 4 different alloys compositions shown in this figure. And so these are all relevant to designing device layers in order to obtain good solar cell efficiencies. This shows some physics about the direct and indirect band gap. So in the direct band gap material, the conduction band minimum is directly above the valence band maximum in K space zone. And so then you have direct photon absorption. And in the indirect band gap materials, you have phonon-assisted photon absorption, which is much weaker. So that is the basic difference. And typically, direct bandgap materials are preferred for many kinds of solar cells. However, there are conflicting requirements in terms of cost versus design that can make it necessary to consider different kinds of materials for different kinds of solar cell requirements based on the segment and the specific design goals that the solar cell is trying to meet. And so after the absorption and the photogeneration of carriers, there is also recombination. So these photogenerated electrons and holes can also recombine. Recombinations of different types. So on the right, we show this radiative recombination process, which has a mass action law kind of dependence on holes concentration and electron concentration. And then we have various non-radiative recombinations, like on the left, we have the Shockley-Reed-Hall type of recombinations, which is mediated by defects in these materials. And we also have a 3-particle or 3-carrier kind of dependence for this Auger mechanism of recombination as well. So in the radiative recombination process, the electron in the conduction band recombines with the hole in the valence band and emits the energy as a photon again. So this is, in the solar cell, this is basically a re-emission of photon. And this is a re-emission of above band gap photon in this radiative recombination process. While in the non-radiative recombination process, which can be mediated, for example, by defects with mid-gap states. The recombination takes place with emission of sub-band gap energy or below band gap energy. So that energy is basically lost and cannot be retrieved again inside the solar cell. And then you have the Auger recombination. And the total recombination rate is the sum of all these different kinds of recombination rates. And so as we try to make the photogenerated carriers drift and get collected in order to get electrical energy out of these solar cells, these recombinations basically try to hamper that process. And so we need to typically minimize recombinations. As we mentioned, the radiative recombination re-emits a above band gap photon, and that photon can again be reabsorbed. So to some extent, the radiative recombination processes aren't all that bad. So the non-radiative recombination processes are the ones which cause maximum loss of energy, and we need to minimize those specifically. However, we need to focus on minimizing all kinds of recombination processes, but specifically the non-radiative recombination processes, the rates. Then we also have surface recombination, which has which is given by this kind of integral, which is basically due to gap surface states, for example. Then we have the various device current transport equations that determine current flow in these materials under elimination, for example. And we have an electron drift term, a hole drift term. Then we have electron diffusion terms and hole diffusion terms as well. And then we have various electrostatic and electrodynamic equations. Then we have a hole current continuity equation, which has the generation rate, which is basically the electron hole pair generation rate coming from incident solar radiation, and then the recombination rate, and then the variation of hole density with time. And similarly, there is a continuity equation for electrons. And then we have various electrostatic and electrodynamic equations that determine the band bending due to charge profile, net charge profile in these materials. And the net charge profile is determined by the hole concentration, the electron concentration, the charged impurity concentrations, and other impurity concentrations in these materials. And then we have the continuity equation when written in terms of the drift and diffusion terms looks like this. And then there is the generation recombination terms, and then we have a steady state. We can transients in these devices. Then in the steady state, it looks something like this. And then we have the similar things for the electrons. We have the hole terms and the hole equations and the electron equations. These equations basically all go into determining the kind of current density profile in these materials as a function of position, and in determining the net current that flows in these devices. And so the basic material, one basic material physics is the absorption coefficient that determines the various generation rates as a function of position in these materials. Then we, of course, have mobility and diffusion coefficients and recombination rates that are also material parameters that also vary with material composition and with the material system. And that needs to be kept in mind while designing these devices, while optimizing these devices to get maximum solar cell conversion efficiencies. So some more details about re-emission and reabsorption physics. So the re-emission by spontaneous emission is random in direction and can lead to overall loss of photons from the device. However, as we mentioned, the radiative recombination is above band gap radiation, which some of which can be retrieved. So it will lead to some overall loss of photons, but some of it can be retrieved. While this is not true for non-radiative recombination. So we need to specifically minimize non-radiative recombination during solar cell operation, but we also need to keep in mind the details about the radiative recombination. And so these are some of the re-emission and reabsorption physics that's taking place inside these materials and inside these solar cell structures. Have some more spontaneous emission physics, and these are photoluminescence efficiencies in various kinds of materials, and we have different kinds of grown gallium nitride, and similar kind of things can be seen for the alloy systems. And we have the photoluminescence band coming from above band gap transitions, but we also have these defect cause transitions that are can be due to deep states or due to acceptor and donor impurities. So we have these donor bound excitons as well. So we have these exciton levels, and then we have these other above band gap trends. And these photoluminescence, which are basically experiments done on these materials, give some indication of the kind of things you can expect when it comes to the recombination terms that occur during solar cell operation. So there is the generation term due to absorption of solar radiation photons, but then the recombination terms look somewhat like these. And this is the physics behind those terms. And so the deep states can affect spontaneous emission characteristics through non-radiative recombination. In this slide, we mention a different version of this solar cell design called the tandem indium gallium nitride solar cell. So we have different subcells, and in this, we first show this subcell, which basically looks similar to the cell shown in the previous slide. We have the lighter photon absorption layer and the dark current reducing layers, and then the front reflective contacts, etc. But then we repeat these structures with a lower band gap of indium gallium nitride and then an even lower band gap of indium gallium nitride. So we have high band gap and then low band gap of indium gallium nitride in the sequence from the direction from which the solar photons are incident. And when we repeat these structures, these different layers, of course, typically have different indium and gallium composition. Now, this is each subcell. So we can have 3 or 4 subcells which focus on absorbing different parts of the solar radiation spectrum. So the dark currents, the short circuit currents, and the fill factors of each cell in the tandem cell must be optimized for overall high energy conversion efficiency, these materials. So the basic physics is that each subcell in this tandem cell focuses on a specific part of the solar spectrum and then tries to convert as much of the absorbed solar photon energy into electrical power, into current and voltage combinations of electrical power without losing energy to the lattice, losing energy to lattice vibrations or phonons, for example, in these materials. Now, that is the basic concern behind tandem indium gallium nitride solar cells. Now, when we repeat these structures, we have to interface these subcells, and then we need to make sure that there is the good interfacing so that there is minimum voltage drop at the interfaces of these subcells. So that is a design consideration that needs to be kept in mind, and that typically involves what are called tunnel junctions that we need to optimize in order to get good tandem indium gallium nitride solar cell designs. Some more physics about what enters into the tunnel junctions that go into making these tandem cells. So we have acceptor ionization, and then we have hole concentration, and we have tunnel junctions. So we have the conduction. So we have shown here the conduction band edge, valence band edge, and then the donor and acceptor energy levels. These are not exactly to scale, but they basically mention the location of these donor and acceptor energy levels in millielectron volts relative to the conduction and valence band edges. So we have the donor energy levels, which is about 40 to 60 millielectron volts below the conduction band edge, and then the acceptor energy level, which can be 150 to 160 millielectron volts above the valence band edge. For large gallium concentration, that is the case. And the large, the fairly large, location of the acceptor energy level above the valence band edge, which is 150 to 160 millielectron volts, is several times the thermal energy at room temperature. And that means that typically the Fermi level remains well above the valence band edge in these materials for a wide range of temperatures. So on the right, we show at different temperatures, the Fermi level location as a function of temperature for large gallium concentration in these materials. And we can see that the Fermi level remains fairly high above the valence band edge. Then that means that only a small portion of the physical acceptor doping concentration is actually ionized and leads to mobile hole carriers in these materials. And that is a concern when we try to design tunnel junctions for the tandem cells in these kind of material system. Physics of generation rates and quantum efficiencies in these materials. So the absorption coefficient is a function of position because there is composition grading. Quasi-continuous grading can have some spatial averaging effects on the dielectric function, as typically the generation rate is determined by the incident intensity and then the absorption coefficient in these materials. Then the incident intensity typically varies from the top of the solar cell as we go towards the bottom of the solar cell. This material through this exponential kind of variation dependence due to the absorption that takes place in this material. Now, the quasi-continuous grading can have spatial averaging effects on the absorption rates, and that is a physics to keep in mind while determining efficiencies. Now, this dependence of intensity and then this generation rate as a function of intensity profile in these materials are what gives the generation rate as a function of position in the various device equations that we discussed in previous slides. And those are the generation rates that go into determining short circuit currents, etc., and then determining the currents and voltages that we can get out of these devices under solar cell operation. Now the same implications of quasi-continuous grading also hold for spontaneous emission in these devices. So those are the basic physics of generation rates and quantum efficiencies in these materials. Now, the grading has an effect on the electromagnetic modes that are operating in these devices, and it is these electromagnetic modes that propagate in these devices. When we have incident solar radiation, they get transformed into certain electromagnetic modes in these devices, and that is determined by the dielectric function in these devices or in these device layers. Now, to keep in mind that both the real part of the dielectric function and the imaginary part of the dielectric function are graded in these device layers. And so you can see that the absorption coefficient becomes a function of position in these materials, and especially it becomes a function of the position measured from the top on the direction from which the solar photons are incident. And you can see that the absorption coefficient is a function of the position coordinates and the incident photon energy. And the dielectric function is also a function of position coordinates and the photon energy. And the dielectric function has a real part and imaginary part. The imaginary part especially determines the absorption coefficient, while the real part determines velocity of propagation and dispersion in these materials. But it is the imaginary part which enters into the absorption coefficient, which determines generation rates in these materials. Here we have some details about the various kinds of crystal structures in these materials. We have a woodsite and a cubic crystal structure. Now, this is a schematic, and the actual atomic sizes are different. For example, the red atoms are actually larger in size, but we typically show. So this is the kind of bonding configuration that is seen in these materials. And we have, for example, from the metallic atom, the red atoms, to the nitrogen atoms, which are the green atoms. Then we have the bonds. We have a vertical bond, and we have bonds at angles to the vertical in the woodsite hexagonal version of these materials. And we have unequal bond lengths. And so we have the vertical bond has a different bond length compared to the bond length bonds at an angle to the vertical. And these unequal bond lengths contribute to the to what are called inbuilt or spontaneous polarization in these materials. And then we also have what is called piezoelectric polarization. So the woodsite has spontaneous and piezoelectric polarization, but there is a zinc blend or cubic version of these materials which does not have spontaneous polarization, and they can lead to different device layer optimization designs because the band bending is affected by the built-in polarization-induced charges that arise from polarization grading that take place. So we have this material grading. So material grading also gives rise to spontaneous and piezoelectric polarization grading in these materials. And polarization grading affects band bending and device equations and the overall current voltage characteristics in these devices. And that needs to be kept in mind while optimizing solar cells. Here we show some details about polar and non-polar axis and planes. So even in these woodsite materials, we have the so-called C-axis, and we have, if we have growth along the C-axis or along the 0001 axis, as we say, we get this spontaneous and piezoelectric polarization. But then there are these non-polar axes, or these A planes and the M planes that are shown here, which are perpendicular to the C planes. And if we have growth along those planes, then those are non-polar planes. And then we do not have the spontaneous polarization along the interfacial direction or along the composition grading direction. And that leads to different physical considerations and different material parameters while designing and optimizing solar cells from these devices. Then we have this matrix which involves elastic and piezoelectric constants, and those determine piezoelectric polarizations. We have the spontaneous polarization part and then the piezoelectric polarization part, and that is given by these kinds of matrices that need to be evaluated and that have material parameters that can be calculated and determined experimentally also. Then the strain also modifies the band structure, and then we have the so-called 8-band or 6-band K.P theory. And we have these different terms that enter into the matrix, that is the Hamiltonian matrix that goes into determining the various kinds of band structure that we see. And then that affects the mobility in these materials and other material parameters that enter into the device equations. So this kind of matrices need to be solved in the presence of strain in order to determine the kind of, for example, effective masses that we see. So for example, the effective masses are modified by strain because the band structure is modified by strain, and that affects device parameters and solar cell optimization. This slide shows details about spontaneous and piezoelectric polarization in woodsite material heterostructures and graded layers. So we have, for example, a gallium nitride and then an indium gallium nitride layer. And we have an abrupt heterojunction in this figure. And we have spontaneous polarization in one layer, and then we have spontaneous and piezoelectric polarization in the other layer. And then we have different magnitudes and directions for these spontaneous polarization. Now, this is a specific combination, which is shown for a specific heterojunction. And then we can have other combinations for different kinds of strained and unstrained and compressive strain and tensile strain in these materials. So as we have different material combinations and different epilayers and substrate combinations or different kinds of epilayer heterojunction combinations, we have different combinations for these polarization magnitudes and directions. Then we can have quasi-continuous grading, and that also gives rise to position-dependent spontaneous and piezoelectric polarization, and that again enters into device equations and into the solar cell characteristics. So in graded woodsite materials, we have this kind of spontaneous and piezoelectric polarization, and they are a function of position. And we have these kinds of magnitudes and directions for these components of polarization. And so the position-dependent spontaneous and piezoelectric polarization lead bound charge densities as well, and those affect device characteristics. This slide discusses some spontaneous polarization physics as a function of lattice parameters. So you can see that in the nitride semiconductor system, the group 3 nitride semiconductor system, as a function of the A lattice constant, which is the lateral lattice constant in the hexagonal plane. This has a complicated dependence, while it has a much clearer dependence on the vertical lattice constant, or the lattice constant along the C-axis. So those can be calculated from band structure calculations also, band calculations, and that can be determined experimentally also using various kinds of heterojunction layers. For example, we can experimentally determine the spontaneous polarization parameters and then correlate them with the lattice parameter. These are some typical magnitudes of spontaneous and piezoelectric polarization as we vary indium and concentration in these materials. You can see you can have some Boeing dependence, and those all need to be entered into the device equations in order to predict and to understand the device characteristics and to understand the solar cell power conversion efficiencies, for example, as a function of the various kinds of device layer designs and device layer gradings that we use in these materials. So as we mentioned, we have, for example, non-radiative recombination that needs to be low in these solar cells, and we have deep states due to dislocations from these materials, for example. And this slide shows some typical dislocation density as a function of thickness for different growth substrate growth methods in these materials. And we have these different kinds of chemical reactions that enter into, for example, one kind of substrate growth methods. And those are some details about dislocations versus substrate growth. Silicon carbide substrate on which we can grow these materials, or we can have silicon substrates. So those are all cost versus device performance considerations that need to be kept in mind while designing solar cells for different application segments. We have indium gallium nitride growth technology, and we have these different kinds of morphologies of group 3 nitride semiconductors under different growth conditions. And those are some details for determining things like, for example, dislocation densities, recombination rates in these materials and in these solar cells. Some more about layer width design. So the layer width design has to be done along with material composition, the material grading design. Now, the consideration is that we want to absorb all of the incident solar radiation and most of it to be collected, or that means the photogenerated carrier should not recombine too fast. We need to minimize dislocations in these materials. We need to minimize any kinds of deep states, for example, due to vacancies in these materials. So those are all, again, material considerations that go to deciding device characteristics and solar cell optimization. And then there is exciton dissociation considerations. So the electrons and holes that are generated by these incident solar photons have a Coulombic attraction. So the conduction band electron and the valence band holes have Coulombic attraction, and due to that, they can form a bound state, which is called an exciton, and that has a certain dissociation energy or binding energy. Now, if we have large gallium composition, that binding energy can become higher than the thermal energy at room temperature. For example, the thermal energy near room temperature is something like 25 to 26 millielectron volts, while for large gallium composition, the exciton binding energy can become something like 40 millielectron volts. What that means is that the excitons aren't dissociated thermally once they are formed in these materials with high gallium composition, indium gallium nitride. And so we need to somehow dissociate these excitons, and that is done by the built-in electric fields. So the electric field magnitude, etc., needs to be large in order to dissociate the excitons, and then these dissociated excitons can then mean that the conduction band electrons and the valence band holes can drift in opposite directions. And that is necessary for obtaining good photoresponse and for obtaining good power conversion efficiency in the solar cells. So this excitant physics is key to obtaining good solar cell performance in this material system. Then we show here some experimental data about excitant physics in these materials. We have photoluminescence intensity as a function of photon energy, and we have different kinds of donor bound excitons, acceptor bound excitons, other excitons in these materials as a function of photon energy. And then on the right, we have these, there is the excitonic peak near the absorption edge, the band gap absorption edge in these materials for different compositions in these materials. And so those are, as we mentioned, the excitons need to be dissociated by the electric fields in order to lead to good transport of electrons and holes. So that excitant physics has to be optimized also in order to obtain good solar cell conversion efficiency in these materials. Then we have the electromagnetic wave propagation with the excitonic levels, and we have the so-called polaritons. And we have, for example, the dielectric function along with the excitonic contribution. Then we have the electromagnetic wave propagation with this kind of dielectric function. And then this electromagnetic propagation can split into modes, and we have the so-called upper polaritonic branch, lower polaritonic branch. And those are the kinds of modes that actually propagate in these devices close to the band edge, for example. And you can see that these are some of the, on the right, you can see that these are some of the experimentally determined mode energies as a function of the wave vector in these materials. So we have the dispersion of the electromagnetic wave as a function of the energy as a function of wave vector, or the frequency as a function of wave vector, and that splits into these branches, or these polaritonic branches, due to these excitonic levels. And this is again a consideration for designing solar cells. This slide talks more about power conversion efficiencies and the specific forms of the current voltage characteristics. So we have shown here is typical current voltage characteristics under illumination. And under illumination, you can see that there is a short circuit current, and then there is an open circuit voltage. And then when you drive a load, the voltages and currents are somewhere in between the open circuit voltage and short circuit current. And there is a specific combination which leads to maximization of power or power conversion efficiency. And that is the maximum power conversion efficiency we are looking at to get good solar cell characteristics. But there is a so-called Shockley-Queisser limit, which is there for single junction solar cells. And we have the equation for that shown on the bottom of the figure here. And so it is the limit which is there for single junctions. So it basically says that for single junction solar cells or single junction photovoltaic cells, the maximum power conversion efficiency can get to something like 31 to 33% as we vary the semiconductor materials. However, we can use multi-junction tandem design. So we discussed some of the tandem cell designs in a previous slide, and they can lead to higher efficiencies. So the tandem cell designs have multiple junctions, and so they can help overcome the shock-like quasar limit and lead to higher efficiencies. Now, composition grading that we mentioned as one of the major design features in this talk can also help achieve some of those same advantages. So the basic idea is that you focus on absorbing specific parts of the solar radiation in specific parts of the solar cell, and then you convert as much of it to electrical energy without losses to the semiconductor lattice. So those are the basic considerations for multi-junction or composition graded solar cells made from the indium gallium nitride material system. This slide we show some quantum efficiency numbers calculated for one solar cell design in these materials. So you can have depletion width in these materials, and then you can have quantum efficiencies for different incident photons. So you can see these different photon energies, and you can see that they have different quantum efficiencies as a function of depletion width. And those all enter into determining how we grade these materials and what kind of drift layers we have and dark current reducing layers we have in order to obtain good power conversion efficiencies from these solar cells. Now, an average quantum efficiency can be calculated for incident AM 1.5 solar radiation also for different kinds of solar cell designs. So in conclusion, we have that indium gallium nitride composition grading leads to large polarization induced. And those affect device design, band bending profiles, and current voltage in these solar cells. The cubic indium gallium nitride has the potential to offer higher efficiency. However, the woodside crystal structure is thermodynamically more stable. So it is more prevalent technologically, the woodside crystal structure, and it is technologically more difficult to obtain cubic indium gallium nitride. And we need optimization of growth to obtain these different kinds of crystal structures. Now, the woodside structure typically grows on, for example, the 0001 plane of the crystal direction, crystallographic direction, while the cubic structure grows on, for example, 001 substrates. So we need optimization of growth on 001 substrates in order to obtain the cubic version of the indium gallium nitride material in order to get some advantages for solar cell optimization using the cubic versions. So those are all research topics for obtaining good solar cell characteristics in indium gallium nitride material system. And then we also need to optimize p-type doping for these for tandem cells when we use multi-junction designs using this material system. We have some details about epitaxial growth mechanisms and methods in this for this material system. We have, for example, metal organic chemical vapor deposition. We have the metal organic sources. Then we have the dopant sources. And then we have the reaction at the surface of the substrate. And then we grow these different kinds of epitaxial layers by varying these flow rates and varying the different growth conditions. And then we want to, for example, keep dislocation densities low, and we want to get the right material composition and the right dislocation densities in order to get a good solar cell. These are some more details about the metal organic emissivity growth method. We also have the molecular beam epitaxy method. We have the fusion cells, and then we have a RF plasma nitrogen source. We have the growth monitoring by a read gun or a reflection high energy electron diffraction source. And so we have an high vacuum, ultra high vacuum environment in which these atoms come and then deposit and form these epilayers on top of the substrate. And then we again want to optimize things like dislocation density, doping profile density, polarization grading in these materials in order to obtain good solar cell characteristics. We also have the hydride vapor phase epitaxy that can be used to form these epilayers. So we have these different epitaxial growth methods for obtaining solar cells from these materials. Here we mention some basics about dislocations that we mentioned, which are centers for non-radiative recognition. So typically this indium gallium nitride material system has the woodside crystal structure, but here we show some schematic for example, an edge dislocation and then a skew dislocation in these material system. And we have the so-called Burgers vector characterizing this material system, these dislocations in this material system. And then these dislocations introduce deep states. So for example, they have dangling bonds and they introduce mid-gap states or deep states, and those can lead to non-radiative recombination, and we need to minimize those. So reducing dislocation density is a key consideration when designing these solar cells. And as we saw in some previous slides, the dislocation densities can be affected a lot by the substrates that it used. For example, silicon carbide substrate or silicon substrate or sapphire substrate can lead to different kinds of dislocation densities. And also the growth conditions can affect the dislocation density. So those need to be optimized for obtaining good solar cell performance. More details about tandem cells. The tandem cells need good tunnel junctions. So here we show a typical tandem cell configuration. This is actually in a different material system, but it looks kind of similar in the indium gallium nitride material system. And we showed some of this typical diagram for the indium gallium nitride system in a previous slide. But as you can see, we have these P++, N++ tunnel junctions in these materials that go into determining the interfacial characteristics of between these subcells. And so we have voltage drops between these subcells, and we need to make sure that these voltage drops are small so that we get the maximum power conversion efficiencies. And so we need low contact resistance tunnel junctions. And so those are things that need to be kept in mind while designing these tandem cells in this indium gallium nitride solar system. And as we mentioned, because the P layer is difficult to get more P concentration out of due to deep acceptors in these material systems, we need to specifically tailor the band profiles in these tunnel junctions to get good tunnel junction contact resistances, etc. And so this is a major design consideration, and especially in this material system while designing tandem cells. Then we have the so-called critical thickness for epilayer growth. So when we grow one epilayer on top of another, on top of a substrate, for low thicknesses of epilayer, the lattice constant of the epilayer tends to adjust to the underlying lattice constant. And so it becomes strained. And it is in these strained layers that we have what is called piezoelectric polarization. Now you have to keep in mind that as we increase the epilayer thickness, there is a competition between the strain energy that is there in this strained layer and the strain energy that is associated with dislocations, if dislocations are formed in these materials. And when the strain layer energy becomes larger than the energy associated with dislocations, then the epilayer relaxes and forms dislocations, and it relaxes to its natural lattice constant, and then it is no longer at the lattice constant of the underlying substrate or of the underlying epilayer. And when this happens, the piezoelectric polarization goes away. So we need to keep in mind what are the critical thicknesses in this material so that we know whether or not we have piezoelectric polarization and how much of piezoelectric polarization we have in these materials as a function of layer thicknesses and as a function of composition grading in these materials. So the various force and energy terms that enter into determining what are the critical thicknesses involve the, for example, different elastic constant parameters in these elasticity constant parameters in these materials, and then the Budger's vectors, and then the dislocation dimensions, etc. And those enter into theoretical models or semi-empirical models from which critical thicknesses can be determined and then can be compared with experimental values. Now, the different models can predict critical thicknesses for equilibrium. However, we need to keep in mind that growth can have non-equilibrium components, and so the critical thicknesses can vary from these theoretical predictions. So these non-equilibrium determined critical thicknesses, and those basically determine the critical thickness and piezoelectric polarization in the materials. For example, we have a so-called Matthews-Blakeslee model, then we have a People-Bean model, another kind of model. Then we have a so-called Van der Merwe model, which predict these critical thicknesses. However, the non-equilibrium kinetics can affect the critical thickness, and they can be much different from what is predicted by these equilibrium theories. So we have these elastic parameters and dislocation dimension parameters, Berger vector parameters that enter into determining these critical thicknesses. And then we need to keep in mind that when we have quasi-continuous grading, the critical thickness can vary from these abrupt heterojunction kind of critical thickness predictions. So those all need to be kept in mind while designing the solar cells and for getting low dislocation densities, and for getting understanding and optimizing the piezoelectric polarization component of the polarization grading. So there is the spontaneous component, but the piezoelectric polarization component depends on the critical thickness and on the level of strain in these different epi layers and in these different graded layers. Growth kinetics affects critical thickness, and that we can correlate theory with experiment. We have these so-called transparent conducting oxides in these materials for contacts in these solar cells in these material systems. So we have indium oxide, tin oxide, and zinc oxide, and different combinations of those. And those can be used to get transparent conductive oxides. And we have contact technologies. So as we mentioned previously, there is a plasmon frequency or the plasma frequency, which determines the dielectric function variation with frequency and the kind of reflections and the absorption that we get in these transparent conducting electrodes. So the next slide shows some typical band structures of transparent conducting oxides. So these band structures determine things like effective mass, as well as dielectric functions, and then these determine things like the plasmon frequency, and then the dielectric function and the kind of reflectance we get. And we typically want low reflectance, and these transparent conducting oxides from these material systems can be used to obtain low reflectance transparent conducting oxides for use as front contacts in these solar cells. This slide shows some typical absorption coefficients and transmission coefficients in these transparent conducting electrodes made from these materials. Talk some more about one of the previous slides. So stay on this slide because it shows different material compositions, for example, different indium compositions in indium gallium nitride. This slide shows absorption coefficient. You have to keep in mind that we have these kind of material parameter variation as we vary the indium composition in indium gallium nitride or the gallium composition material system as for different things like effective mass and for scattering rates and the mobilities in these materials. And then especially as we vary as the effective mass varies, for example, the acceptor binding energy also is different. And for large gallium composition, the effective mass is larger and the acceptor binding energy is larger, and that leads to lower ionization of acceptors, and that leads to lower hole concentrations. That means getting good tunnel junctions in tandem cells is different, and also getting good contacts to the P layer in just the graded layer solar cell designs is also more difficult. And so those need care, those cases need careful design in order to obtain the desired level of solar cell power conversion efficiency and optimization. So that concludes the talk about position graded indium gallium nitride solar cells. Covered physics of indium gallium nitride photovoltaic cells with different kinds of